Okay, so I was just thinking the other day that I may have been kind of teaching this more like a math class, and I'm not sure how many of you really know what it is you're doing. What I mean by that is you know how to do the steps, but you don't know, you don't have any, it doesn't have any meaning to you. Would you feel like that's kind of where you're at? Okay, so let me try to put this into context here using this bell ringer here. Okay, it says 32 grams of KClO3. So what that's saying is I were to go into a lab and I had 32 grams of that particular reactant. Okay, and I wanted to decompose it into these two products based on this chemical equation. Okay. What I can do with stoichiometry, and the whole purpose of stoichiometry, is to predict either how much product you're going to produce, how much reactants you would need to react with another reactant. You could predict if you wanted to produce this much product, how much reactants you would have to use to produce that much product. So what you're doing here is we're using math to be able to predict what we want. So like, for example, let's say I wanted to go into a lab and I wanted to produce a certain amount of oxygen. I'll make it up. Let's say I wanted to produce 60 grams of oxygen by decomposing this. Okay? I can figure out exactly how much of this I would need to do it using the math. Let me show you. Now, would there be an applicable purpose to be able to say, this is how much product I want? Is that something that would make logical sense for maybe a production company or someone who's doing research or whatever? Would that be a reasonable question to ask? Okay? And so I say, I want this much grams of O2 using this particular reaction. So what I want to do is use stoichiometry to figure out how much of this I have to decompose to get 60 grams of oxygen gas. Okay? So, what I can do is I can set up a 3-step problem and figure out exactly how much mass of KClO3 I would need. Okay? We know that everything goes through the mole train when you're trying to go from one substance to another substance, correct? So my first step would be to take this and convert it to what? Moles. I'm assuming at this point we're pretty good. 32, 2 times 16, yeah?
Yeah.
Okay. And the whole purpose of this second step, which is the mole ratio, is because I'm specifically trying to get O2 from this decomposition reaction. Does that make sense? Are there other ways to get O2?
Yeah.
Absolutely. But in the context of what I'm trying to do, I'm using that equation. So I'm going to use that recipe to be able to figure out how much of it I need to decompose. Does that make sense? Huh? Yep.
Yeah.
Yep. What do we got? KCl3. And we got a 2 to 3 ratio, correct?
Opposite of what the dollar is.
Yeah, the reason why I chose this is to kind of show you what we're doing, right? The applicable purpose of this, where you would see it happen, okay? Then, I would take it, I would convert this moles to what? Grams. Now, does somebody have that molar mass handy? Actually, I'd rather do
122.46.
I have 5.5.
So do I. Oh, well.
Okay, so let's see. Let me just do that real quickly. $153.18. So someone make sense of this answer for me. What is that? What is that? What did we just do? What was the purpose of this? What does that tell us?
To get 60 grams of oxygen, you need 153 and 1,800 potassium chloride oxide.
Okay? If I want to produce 60 grams of oxygen, using this equation, using this method, I would have to go into the lab, I would have to pull out this much of KClO3, and I would have to decompose it. That's what we're doing. Okay, some of you are like, I really don't care. But I just wanted to give you a reason for what we're doing. We're not just throwing numbers around. Now, if you were to actually go do this in a lab, do you think you would actually get 103.18? No, you're probably going to get less. Why?
Because every time something becomes unusable.
Well, yeah, there's going to be some error involved. Okay, we also haven't talked about that not all reactions go to completion. That's later on in this semester.
How
Okay?
do you get how much you want?
You have to know something about equilibrium.
That's not.
Okay, what you'll find in chemistry is it's not just one thing that you have to know to be able to do a lot of the chemistry things. There's so many things. For example, you could have something that's thermodynamically favorable. What I mean is, from an energy standpoint, it's very favorable. Like, and very imagine the most exothermic reaction you could think of. Okay? Even if it's spontaneous from an energy standpoint, doesn't mean that it's fast. What I mean by that is, diamond decomposes into carbon spontaneously. But, you know, ladies aren't walking around, and while they're walking around, the diamonds on their hands aren't turning into coal, are they? No. And the reason why is that the process happens so slow. So you can know as much as you need about stoichiometry, but if you don't tie it to the other things in chemistry, you don't have the whole picture. We're going to talk in a couple of chapters about rates, how fast things react, and what plays into that. Okay, so what we're doing here is, it's not one area that makes you really good at chemistry. It's a big, broad spectrum that actually works really neatly together. Okay, and I know you guys probably don't understand that yet, may never understand that, but from what I know, it's pretty cool. So, you ready to do living reactants? Something we haven't really touched on yet? Okay, I can go back, guys, to our Rice Krispie example, right? Say we go back to our Rice Krispie example, and I don't remember the exact amount. Let's see if I remember. What was it? 6 cups. We had 3 tablespoons, and we said that's how many tablespoons. And we said, what was the other thing? 40 marshmallows. Right? Got it? And you go into your cupboard, and you find that you only have 4.5 cups of cereal. We said that was a problem, right?
That would be the limit.
Okay? We had to do one of 2 things. We either had to scale down the recipe, or we're going to have to go to the store to get some more ingredients, correct? Okay? But if I go into the cabinet and I see that I have 4.5 cups, I have 5 tablespoons of butter, and I have 80 marshmallows. From a marshmallow standpoint, aren't I going to be able to make 48 Rice Krispie treats? If you just think about from the marshmallow standpoint, absolutely, right? And from the butter standpoint, I'm going to be able to make quite a bit more than 24, right? I don't know the exact ratio off the top of my head. Okay, but the point I'm trying to get here is there's a particular ingredient that's doing what?
Running out.
It will run out. Now let's say I had a reaction. A plus B produces C. If A runs out, does it matter how much B you have?
No.
Are you going to produce any more C?
No.
No. That is the idea of limiting reactants. Okay? If one of your reactants runs out, you can no longer produce any more reactant products, no matter how much of the other reactants you have. Okay? Do you remember the problems where it said you had this many grams of this thing, and then it says you reacted with excess something? What that was trying to tell you is you had plenty of the other reactant, and the reactant that you were dealing with was going to what? run out. So you knew how much product got produced was dependent upon what? The one that was going to run out. Now what we're going to do today is we're going to have two masses. And you're going to have to determine which one's going to run out first. You with me, Brev? It doesn't look like you are. This is a pretty important, you're going to get lost if you're not paying attention. Okay? Now you can imagine what the excess reaction is, or reactant is. Just by name, what do you think it's going to be? Yeah, you have more than you need, and so you probably have some left over or some excess. Does that make sense? So, let's do this, bro. Okay, I would take copious notes. Okay, so stay with me here because this is going to be fairly complicated. And over the years, there's actually multiple ways to solve these problems. There's a easier, longer way to do it, and there's a harder, less long way to do it. And I found that typically, most times students want me to do the longer, easier version. Okay, so that's what we're going to do. And the reason why I think that's the better way is the other way that's not as long is only not as long half the time. Yeah, it is kind of dumb, but you'll understand. Okay, so if you look up at this particular problem, what is the big thing that should be screaming at you? It looks different than what I've seen before.
What is the limiting reaction?
Okay, that's true.
2 grams.
There's what?
2 things a gram.
There's 2 numbers. Yeah, there's 2 grams, which tells you you're not wrong. You're definitely right. You've never seen limiting reaction up there before. But another way to look at it, because I might not say what is the limiting reactant. You might have to determine it on your own. Okay? Anytime you see 2 masses, you should be thinking limiting reactant. Okay, for the sake of time, I'm just going to give you the equation. Here it is. That's not what that is. So write this in, please.
But to find it yourself, would you have to convert the grams to moles?
Like, it's the same process, but you might not be given that word. Anytime you have 2 reactants, you should assume limiting reactant problem.
Are we supposed to be able to find the thing on the right?
Take on the right.
The product.
Are you supposed to be able to find the product on your own? You could, yeah.
But how do we know what is the place? Like, how do we know?
That's what we have to figure out first.
Oh.
Yep. In fact, the way we do it is we pick a product and we solve for it. Okay? Now, you're not going to know just by looking at these numbers. You might be tempted to think, oh, this is going to be my excess and this is going to be my limiting. Why would one be tempted to think that?
Because it's smaller.
Yeah. But, as you might see, it could be the opposite. Because there's bigger compounds that you have to deal with. Some compounds are bigger than others, and so they have more mass, and so you got to be careful. So here's what we do. Here's the easier way to do this. What we're going to do is we are actually going to take and solve for whatever product we want. Okay? It doesn't ask us for any specific product up here, does it? It just wants us to know the limiting reactant. Okay? So I'm going to actually choose which product I want to solve for. Okay? Which one's going to be easier to solve for? AG. So what we're going to do is we're going to take both of my givens and we're going to solve for that product. Any idea why? If I take this and solve for AG, and I take this and solve for AG, is it possible that one is going to produce less AG?
Yeah,
That's what we're looking for, isn't it? Let's do it.
Wait, can't you?
Can't Get you what?
I was thinking you just put them both into moles.
You can do that.
That's an
I'm going one step further. You could actually figure out moles and do the same thing. But the reason I'm going one step further is because in future problems, you'll be asked to solve for a specific product. And so let's kill two birds with one stone. If that makes sense. Okay?
And when it doesn't, you can just choose whatever.
Like if it just said find the limiting reactant, you would only need to do a two-step problem. You wouldn't need to do a three-step problem. But I'm just gonna go further. Just so that you see. Because isn't the last step for both of these gonna be exactly the same anyways? Alright, we're both solving for AG, so the last step's gonna be exactly the same for both of them. Okay, so let's just start with the top one. We know that these are mass to mass, so it should be bookend molar masses with a mole ratio in between, correct? Everybody with me on that? Okay? I'm going to assume at this point that we're pretty good at identifying what units go where. Okay, so I might go a little bit faster in each individual conversion since we've done this so much. Okay, copper has a molar mass of?
63.55.
Okay? Now we're into the mole ratio step where we got to cancel out moles of desired and go to moles of given and go to moles of desired. What are we desiring? Now, did it say we had to solve for AG? No, we chose that because it didn't specifically say which one to solve for. Just want to know the limiting reactant. Okay, what's the ratio? Okay. Now we've crossed over the bridge. Last step is a molar mass as well, but molar mass of a different substance, correct? Okay. So we got to cancel our moles first, and then grams of Ag. What is the molar mass of Ag?
107.87.
Now, this is going to be the same step over here. I'm just going to put that in. Does it make sense why that's going to be the same step? Okay. All right. Let's do the same thing for AgNO3. For the sake of time, I'm just going to give you the molar mass of AgNO3 here. Because you guys are all good at finding molar mass, right? Most of the time if you get it wrong, it's because you went too fast more than it is you not know what you're doing.
Yeah.
Okay. So 169.88. Okay. We have a different ratio here. Actually, technically, the top from here all the way over should be identical. So this is going to be 2 moles of Ag as well. And then, what do we say? How many moles is this? 2? I'm going to give you enough time to take good notes here. I don't want to run too fast and lose you. Anybody got an answer for the top one?
12.
Yep. 3.8.
Yep.
So what from a conceptual standpoint did we do here?
Oscillating one.
Yeah, but why did we have to solve for the product to do
We
this?
make them like the same.
You
So
have
how much of
a-
the product each one makes?
Yeah, right? If I have 3.5 grams of copper, in the context of this equation, assuming I have enough of the other reactant, right?
Yeah.
This is how much I'll be able to produce. Okay, well, if I got this much of this particular reactant, assuming I had plenty of copper, this is how much product I'd be able to produce. You see the difference here, don't you?
Yeah.
One of them is going to run out first.
AgNO3.
This is going to run out first because it cannot produce as much as the copper can. So our limiting reactant is what?
AgNO3. Is that why there's 2 of them?
I can't get my head around why you can't just do.
But that's still wouldn't be enough. What?
Oh, never mind.
You're talking about not even doing this step?
No, hold on. Let me think.
So this would be the what? Excess reactant, that's what that's representing.
So, yeah.
Figure out the moles.
With it.
So essentially,
Any questions so far?
So is it
that
the
looks
reason the
smaller?
coefficient?
Mhm.
Is that why there's a coefficient of 2 to make it as big as it, or what?
What do you mean?
Like the coefficient of 2 in the equation, is that so that we'll have?
Well, the coefficients are, the purpose of the coefficient is so that we have enough, they have the same amount of atoms on each side.
Yeah.
Absolutely. Okay? And we can figure out exactly how much of this we would need to react completely with this. We could. But we don't have that much, so we're trying to figure out which is the limiting reactant. Okay? Question before we move on to the next one. Yes?
So did you have to pick like the KG? Does it have to be on the right side?
Yes, the one that you pick has to be a product. Okay? For figuring out limiting reactant. Absolutely. Good question. Alright? Now, the reason why I solved for grams, what if this said how much Ag is produced? What would be your answer? This would be your answer. Why is it that?
Because we don't have enough of it to make 12.
I don't have enough of it to make 12. This is going to run out first. As soon as this runs out, will this react anymore? No, it'll just be left over, excess. Okay? So the reason why I did the 3-step here is because in later problems, you're going to be asked, what is the limiting reactant? You're going to be asked, how much of this product will be produced? And then later you'll be asked how much excess is left over, which I haven't covered yet. Want to do that? Sure. Let's do that. Shoot, is that the same equation that I just erased? Oh, probably is.
Do you know how much excess was for that last equation?
No, I mean you could. I could figure it out, but it didn't ask for it, so I didn't. We'll do it in this problem. So here's our equation. This is a significantly simpler equation here. Okay, by looking at this problem, let's identify what are the things it wants to know. It said, what is the mass of Zn produced, and what is the excess left over? What didn't it say?
What's the limit?
Find the limiting reactant. However, you have to find the limiting reactant. Okay? So be careful. It might not say find the limiting reactant, but the big key here is what? Well, that, but probably the bigger key is you have two masses.
There's a way to do
You could do it conceptually in your head, but you wouldn't be able to solve for the numbers.
it. Yeah, but it would eliminate, you don't have to do it twice.
Sure. But I want to see that you can mathematically do that as well. Okay? So what did we say we do when trying to find limiting reactant? What did I say? What did we just do in the previous problem? Okay. Just one, both. What did we do in the previous problem? Right. We took both of our reactant masses and we solved for what? A product, correct? Now, is there a specific? Well, yeah, there is a specific product it wants. What if there was a second product here? Let's just call it product D. Okay. Would we want to take and solve for D? No, we want to solve for the one that it asks us to figure out how much of it will be produced. Does that make sense? Okay. So, we're going to take both of our masses and solve for our product. We're going to kill two birds with one stone. Two Goliaths with one stone. Okay? Zinc molar mass is
65, 63.39.
Now, I didn't kind of intentionally give you a fairly easy one, because what is the mole ratio for both of these? Everything's 1, so I can really just kind of, we'll get to that. But. Has anybody got more mass of zinc sulfide yet?
97.46.
97.46, yep. An amount, got it?
Yeah, 5.2.
Do I have an amen to that?
Mm-hmm.
Okay. We're going to do the same thing for the sulfur. So it is a lot of work. But good thing we've been doing this quite a bit lately, that it should be getting more second nature to us. Sulfur 32.07. Question mark. Okay. Now let me give you a little hint here. You may have been, I've kind of talked about it, but you may have figured this out. When you're trying to find your limiting reactant, the last 3 slots are exactly the same. Because once we cross the bridge, aren't we solving for the exact same thing? So I can say that this is 1, that's 1, and this is 97.4. Now that's when we're taking both of our masses and finding products. And that would be a good idea if we'd actually put the units in. It wouldn't hurt. Okay, anybody get a number for that?
11.
11?
10.6. Oh yeah, you're right.
Alright. So now we have 2 answers here, even though they didn't ask us to find the limiting reactant. So technically they actually only have 1 answer. But they very well could ask you to find the limiting reactant, how much is produced, and so forth. What is the mass of zinc sulfide produced?
5.2. Oh, wait, what?
16.2.
5.2.
5.8.
5.2.
What are you saying?
How much zinc sulfide? What would be the answer to this question here?
5.2.
5.2.
I thought you were asking for the next one. Oh.
5.2. Why?
Because that's how much.
That's how much you can't have enough to.
That's how much you have enough
But
of.
what about the bottom?
That's, you don't have.
That's how much I could produce if I reacted all of this.
Oh.
But which is going to run out? One's going to run out.
Yeah, the one. And it's the one that has
This is going to run out. This is going to go completely to 0, and I'm going to have some left over of this that would have been able to produce 11, but because this ran out first, we're never going to get to 11. Does that make sense?
Do you have to work backwards from 5.2 now?
No. Okay? To find excess, there's a ton of ways to do this. You can work backwards with this and figure out how much of this you would need to produce that much. You could start with 3.5 grams of zinc, and you could solve for sulfur to figure out what would be the correct amount of sulfur that you would need to react with zinc. There's a variety of ways to do this. I usually just say this. When you're trying to find the excess, and you may want to write this down. When you're trying to find the excess, start with your limiting reactant and solve for your excess reactant. When you're trying to find the excess left over, start with your limiting reactant and solve for your excess reactant. Which did we say was our limiting reactant up here?
5.2.
This was my limiting reactant, correct?
Yeah.
So we're going to start with that. And what are we going to solve for?
Sulfur.
Sulfur. For each step problem. Okay? Now, let me give you in context what it is we're doing here. When I take a reactant and solve for another reactant, I'm telling us exactly if I want to react all of my 3.5 grams of zinc, this is how much sulfur I would need to react with it. And I'll explain why that's important for finding excess in a sec. Okay, don't we have all these numbers already in here? Just got to find where they go. Don't we already know the molar mass of zinc? 65.39. Right? Don't we know it's a 1-to-1 ratio? don't we know the molar mass of sulfur?
32.
So you should have all the numbers. You just got to get them in the right spots. Does that make sense? Mass to mass. Molar mass at the beginning, molar mass at the end, mole ratio in the middle. I don't want to go too fast here. I want to make sure that we have enough.
So we've only done problems with 2 reactants. If there's more reactants,
We're not going to do any more than, we'll just do 2.
okay.
Yep. In theory, yes. If you had 3 reactants, you'd have to find the limiting reactant of all 3. But I won't make you do that.
So when you find the limiting reactant, you know the other one's the excess.
Yeah, absolutely. Yep. If you had 3, the other 2 would be in excess.
Yeah.
You'd have 2 excess.
Yeah, that makes sense.
Or maybe that's fine both because it's only two.
Yeah, but I'm not gonna do 3 reactant problems. Okay? We better get a number here.
Yeah.
1.7. Okay. Who can make sense of what we do with that? Or what that is? What is this saying?
It's saying that.
Well, you have 1.7 grams of sulfur.
Left over.
Yeah, you're gonna.
Okay? If I'm gonna react this all the way, which is what we're doing, it's the limiting reactant, correct? This is how much sulfur I would need to react all the way. That's what that means.
So 3.5 minus 3.
So what you're going to do is, this is how much I reacted. Well, how much did I start with?
3.5.
So I started with 3.5 grams of sulfur, and I reacted 1.7 grams of sulfur. So there's a certain amount left over, isn't there?
1.8.
1.8. A lot of work, isn't it?
Yeah.
So let's just quickly, we're not going to have time to do the last problem, which is just another one of the limiting reactant problems. Okay, nothing new. I've kind of covered everything that you're going to see. Okay, so what did we do? At the very beginning, you have to identify what is the, what?
Limiting reactant.
Limiting reactant. To do that, what do you do?
You have to.
What did we do?
You have to solve twice.
Yeah, we had to take our 2 reactants, masses, and solve for the same product. Because what that did is tells us how many of the product we'd be able to produce if we used all of our reactants. Okay? Then we identified the limiting reactant as the one that produces the least amount of product. Right? This is our limiting reactant because it produced the least amount of product. So if you ever have a question that says how much product is produced, you're always going to take the smaller of the 2 numbers. Make sense? Right? I know, it's a lot of work. Okay? Then, if you're asked to find excess left over, what's the key? I had you write it down. What do you got to do?
Start
have to
with the
take-
limiting and solve for your excess reactant.
So we start with our limiting reactant because I know that that's going to run out, so I want to figure out how much of the other reactant I would have to use to make that run out. And then take it and subtract it from what you started with. It's a lot. See y'all in my room after school? How about that?
Probably not. Quarter.
How's that work?
We have play practice. So no.
That's right.
Nuts!